Okay, for question 7, you want to have PC enabled when you're executing and the instruction register enabled when you're fetching. For the address source, case S, basically to be used up here, iFetch when goes to PC, and execute is when the ALU is executing. So basically the way this works is you want to load the instruction when iFetch is enabling the instruction register to be written to, and when PC has the bus. Now PC enable, you want that to be enabled when you're executing because the ALU may need to write to the PC if it's like a branch or a jump, and in that case ALU is going to need access to the PC, so that's why that gets enabled when you're executing. For question 8, you are going to need to stall the pipeline, and that's to avoid two things. The first are jumps or branches. You need to wait for those because the ALU has to finish processing or calculating the number if it's going to be a jump and writing it to the PC before you grab the next PC instruction. So the other one is if there's contention for the bus, if the ALU and memory are trying to write out at the same time, you need to give memory time to finish using the bus to load the next instruction into the instruction register before the ALU can grab it. So for question 9, and basically, sorry, the way you stall in question 8 is just insert a no op. Just have it wait, and that will give time for either the ALU or memory to finish doing whatever it's doing using the bus, calculating the new PC before it continues on. All right, so for question 9, you PC enable because when the opcode is either ALU or ALUI, neither of those need the bus, so the PC can have it. For address source, in case opcode, if you're loading a word or storing a word, that's when you need to give it to the ALU, because the ALU does a calculation and then either stores it or loads it. Otherwise, PC can have the bus. When you're grabbing the instruction, if you're doing a jump, a branch, a load word, or a store word, you need to insert a no op, because any of these these use the bus and they could potentially change the value that you'd grab from memory, and you don't want to grab the wrong instruction. So basically, insert a no op. It basically kills the command that the program counter grab next until the PC is valid, and that's why you wait. So it will be valid the next time you go out and grab it. Otherwise, memory can have the bus and just load up into the instruction register. For question 10, nothing else really needs to be done to the two-stage Princeton pipeline because the no-op gives enough time when store word is used. And store word is the one we're really worried about because with self-modifying code, it does some calculation and then stores the word back in memory in the instruction area like the EDSAC did. But the no-op still gives enough time for store word to execute before the next command's grabbed. So we don't need to do any more changes to this, any more stalls, even if the next instruction that's being used is the one that was just altered. No op gives enough time for that.